You know how sometimes math can feel like its own secret language? Well, today, we're going to crack the code on one of its most powerful parts, exponents and powers. Seriously, this isn't just about crunching numbers. It's a kind of shorthand for talking about things that are unbelievably big or impossibly small. Let's dive in.
So, take a look at this number. That's roughly how many meters the Earth is from the Sun. I mean, writing that out is just tedious, right? And all those zeros are just asking for a typo. But what if I told you there's a much cleaner, way more elegant way to write this?
And that's exactly where exponents come into play. At their heart, they're really just a genius shortcut for repeated multiplication. Instead of writing the same number over and over and over again, we can use this simple, clean little notation. Okay, so let's break this down. It's really just two parts. You've got the base, that's the big number, the one you're actually multiplying. Then you have the exponent, that little number up top. And all it's telling you is how many times to multiply the base by itself. So 6 to the power of 4 is just a much neater way to write 6 times 6 times 6 times 6. Simple as that.
And hey, here's a little pro tip for you, something that'll make you sound like you really know what's up. People mix up exponent and power all the time, but they're slightly different. See, the exponent is just the little number. The power is the whole shebang, the base and the exponent together. So 6 to the fourth is the fourth power of 6. It's a small thing, but it's a cool detail to have in your back pocket.
So if we're saying exponents are a language, then we've got to have some grammar, right? Well, that's what the laws of exponents are. And listen, these aren't just random rules you have to memorize for a test. They're the logic that makes the whole system work so beautifully. Once you get these, you can simplify pretty much anything.
First up, the multiplication rule. This one's a classic. If you're multiplying two powers, and this is the key part, they have the same base, all you do is keep that base and add the exponents together. It's an amazing time saver.
And this shows you why it's not just magic. Look at 5 cubed times 5 squared. If we write it out the long way, you've got 3 5s times 2 5s. So, how many 5s are we multiplying in total? 5 of them, which gives us 5 to the 5th power. The rule just lets you skip all that and jump straight to the answer. 3 plus 2 equals 5. Done.
Now what about division? Well, it follows the same kind of beautiful logic. When you're dividing two powers with the same base, you just keep the base and subtract the exponents. I mean, it just makes sense, right? If multiplying means we add, then dividing must mean we subtract.
Let's see it in action. Say we have 2 to the 7th power divided by 2 to the 3rd. If we write it all out, that's 7 2's on top and 3 2's on the bottom. We can just cancel out 3 pairs of 2's, and what's left? 4 2's on top. In other words, 2 to the 4th power. Or you could just use the shortcut, 7 minus 3 is 4. So much faster.
Okay, so what happens when you get a power inside another power? You know, you've got the parentheses with another exponent on the outside. That's what we call the power of a power rule. It's like you're stacking the exponents. And when you do that, you just keep the base and multiply those exponents together.
Okay, I know that was a lot of rules all at once, so here is a quick cheat sheet for you. We've got multiplication, division, power of a power, even the power of a product rule. Honestly, this is a great slide to just screenshot. Think of it as your go-to guide for the grammar of exponents.
All right, we've got the main rules down. Now let's get into the fun part. The stuff that looks kind of weird at first, but actually has a perfectly logical explanation. I'm talking about zero exponents and even negative ones.
Right? This brings up some good questions. I mean, what does it even mean to multiply a number by itself 0 times? Or -4 times? It feels like it shouldn't work. But believe it or not, the rules we already know actually give us the answer.
And here's the reveal. Any non-zero number raised to the power of 0 is 1, always. Now, you might be thinking, why? Well, think back to our division rule. What's 5 cubed divided by 5 cubed? Anything divided by itself is 1, right? But using our rule, it's also 5 to the power of 3 minus 3, which is 5 to the power of 0. So for the math to stay consistent, a to the power of 0 has to be 1. It's the only answer that works.
Okay, before we jump into negative exponents, we need one quick term, reciprocal. All it means is you flip a number or a fraction. So the reciprocal of 5 is 1 over 5. The reciprocal of, say, 2 over 3 is 3 over 2. Just keep that idea of flipping in your head.
Because that flip is exactly what a negative exponent tells you to do. It's basically an instruction. It's saying, hey, take the base, flip it to the other side of the fraction line, and make me positive. So 2 to the power of -4 becomes 1 over 2 to the power of +4.
So get this, it's not a negative number, it's just a tiny fraction.
And now, we get to the really big payoff. We've learned the language. We know the grammar. Now it's time to see how all this lets us tame those absolutely massive and incredibly tiny numbers that you see all over the place in science.
Remember this monster from the beginning? 150 billion. Using what we now know, we can rewrite it in what's called scientific notation. And just look at how clean that is. 1.5 times 10 to the power of 11. All those zeros are perfectly packed away inside that tiny little exponent. It's just so much tidier, easier to read, and way harder to mess up.
And this is where our negative exponents become superstars. This system is just as powerful for the unbelievably small stuff. A number like this, with tons of zeros after the decimal point, it gets compressed down. That little -9 exponent tells you exactly how small the number is without you having to count all those zeros every single time.
Okay, so this is obviously great for astronomers and physicists. But what about the rest of us? Why should we care? Well, the truth is, this secret language is being spoken all around you, every single day.
The way your savings grow with compound interest, that's exponential. The reason your phone is so powerful is because of Moore's law, which is all about exponential growth in computing. Biologists use it for population growth. It even explains how a meme or a video goes viral on social media. It is literally everywhere.
Let's just ground this with a simple, real-world example. Imagine you stack 5 books, and they're each 20 millimeters thick. Then you add 5 sheets of really thin paper on top. The total thickness is 100.08 millimeters. Now, you don't need scientific notation for a number that small, but we can still write it that way. 1.0008 times 10 to the power of 2. It just shows how the system works on any scale.
And really, this quote just says it all. At the end of the day, that is the job of exponents. They are a fundamental tool that helps us make sense of our world. They make the complicated seem manageable and the unreadable crystal clear.
So, there you have it. You've learned the basics of this secret language of numbers. You can read it, you can write it, you understand its grammar. The only question left is, what are you going to use it to describe? The distance to a galaxy far, far away? The growth of your money in the bank? Or maybe the size of a single atom? The possibilities are, well, they're exponentially large.